You might just not see the bottom inch of the slide. Okay, so welcome to Site Reliability Engineering at Google, or sort of an overview of, today we're going to talk about a couple internal Google technologies that I find very interesting and fun to play with, and I thought I'd share them with you. So I want to give some credit where credit's due. I didn't invent any of this. I'm just a user. So no, oh wow, he's so brilliant. He invented MapReduce. No, did not. At Google, system administrators are called site reliability engineers, and that is to put the focus on what's important about what we're doing. People a lot of times they ask me what's it really like inside Google. There's a lot of rumors, and some of them are widely inaccurate, and some of them are, boy, are they off base in the direction we wouldn't have expected. So yes, all site reliability engineers did recently receive leather jackets. That's with a patch, and each year of this leather jacket program, you can get a different patch. People say, why did everyone get leather jackets? I like to think it's just because we look so good in them. That was a little egotistical. So, oh, the video monitor is really not that.
Well, why don't we?
Is there an auto adjust on here? Maybe?
Yeah.
Move it up a little bit.
I'm going to keep going while Trey does this, because these are just some fun visuals. This is a picture of the campus in Mountain View, or our headquarters in Mountain View, California. It's a very big campus. It's the, those buildings used to be SGI. As SGI. In fact, there's at least one employee that sits in the same exact office as when he was working there at SGI. You know, the other SGI building is the one, the executive center that they opened right before they tanked. That's now the Computer History Museum. And
there is an SGI employee in the room, not me.
I know. Well, tanked, but you're back. You're now.
Out of Mountain View too.
Okay. Well, that looks better. No.
Right.
4 hours.
This,
4 hours.
Yeah, I think.
Like, I imagine there are AV conferences, and when their projectors don't work, you get the whole audience.
That's why I never buy that.
No.
Yeah, there, that's better. Perfect.
yeah, there we go.
This is uniform.
Yeah.
Back to signal.
Is it a Mac or a Linux box?
It's Mac.
Okay. Now, you see
Oh,
where
that's
it's
good.
red?
That's good. Wait, let me detect this.
Yeah, detect.
Yeah, I'm still
Yeah.
missing.
You see where it says go to PC adjust in red? You want to go to the right. There you go. Keep going. Keep going. There. Okay, now go
It's
up.
on position though.
That's position, not
Not size.
size.
Have you tried restarting it yet?
It's really okay.
Every time?
Turn it off and then turn it on again.
Yeah, sorry.
You know, it might-
Try Dutch.
It might be.
If it was a Google
What was it,
projector,
up
it
and
would
down
be
line?
half the size and it would poop unicorns.
Reset all settings.
Oh,
Oh,
That's worse.
don't worry about it. Just sit down.
I just made it worse though. Is that worse? That's worse, isn't it?
No, it's worse.
Yeah.
Yeah. Go back.
What's auto image?
Nope.
Yeah, you hit that. You set it to true.
Yeah, I did.
And
Set
now
it
you're
to keystone.
Keystone. Yeah. Sorry.
Okay, well, we'll work with it. Okay, so we have offices all around the world. I used to be on the team that opened these offices. It's very fun. Though I never traveled to open an office. We packed everything in a box, shipped it out, and all someone locally needed to do is, well, the shipping people moved the rack into the right room and power it up and really configure it remotely. We're a dog-friendly company. You're allowed to bring your dogs to work.
Even pit bulls?
Well, then you'd have to turn to the policy that says one strike and the dog's out. We do get our meals provided. We have 3 meals a day in some very nice cafeterias. Sometimes we have guest chefs come to our cafeteria. Lots of different perks. And oh, I'm not supposed to talk about the moon phase. But, and one of the really nice things about Google culture is we have company-wide engineering standards that we actually follow. So when I was at a certain large telecom, you know, engineering departments say, oh, we're all going to use, you know, capital letters, and I'm going to be like, what? And ignore it. But here we really do all use the same source code repository, we use same build system, release processes. It's really quite a dream from that perspective. Now the mission of Google is to organize the world's information and make it universally accessible and useful. And every Google employee can quote this, and it's important. Unlike a lot of corporate missions, mission statements, we actually do use this as a guide. I mean, you know if you're in the right direction if you're doing something like this. And I bring it up in this talk because the world has a lot of information, and really this talk is about dealing with large amounts of information. Technically, what makes Google so interesting is our speed, reliability, and dealing with big data. Google is fast. Google returns our search results in under 200 milliseconds, and we're proud of that. And if you notice on the web page in the corner, it tells you how many milliseconds it took to return those results. People have been known to say things like, oh yeah, I'll be there in 10 seconds. And it's, really? You mean 1,000 milliseconds? It's reliable. Google is always up. When ISPs have problems, we get complaints because people just, if their homepage is set to Google and they can't get to it, they just assume Google is the internet, and the internet is as reliable as Google. So the old standard used to be, you know, as reliable as the phone system. We think it's now, well, as reliable as getting the Google homepage in many cases. And we're dealing with big data sets, really big data sets. The name Google is sort of a pun on the term Google, which is 10 to the power of, it's a 1 followed by 100 zeros. Google has large computational requirements, and the reason for this is there's actual business drivers. We don't just do it because it's fun. We find that with more data, we get better results, and with better results, people come to us more. So we get more queries, and we use those queries to drive more data, which gets better results. And so it's a cycle. And the traffic never stops. We get thousands of queries per second, even at 2 a.m., even on Christmas morning. So, can't figure out PowerPoint enough to shut off some of these animations. So the Google technology stack has services on the top, in the middle, the distributed computation infrastructure, and at the bottom is our computing platform, the computers and networks themselves. What we're going to talk about today is mostly in that middle section, MapReduce, Sawzall, and GFS. Oh, and we're also going to talk about using cheap PC hardware. So I guess it's a well-known fact, but yes, Google uses Linux. When you say, oh, you know, I use Linux, but you know, my grandmother doesn't. Well, if she uses Google, she's using Linux. So it's Linux on, sorry, it's applications on top of things like Sawzall and GFS on top of it. The structure of this talk, first I'm going to talk about the machines, then I'm going to talk about the data, and then I'm going to talk about how we manage our services. the economics of web farms. More machines equals more reliability, which is sort of backwards. One would normally think if we have more machines, then there's more of a chance that one machine will be down. And that's true. But when we have more machines, we can engineer it such that the user receives more reliability. So when you have more machines, everything can fail. Everything can fail. Power strips, Ethernet cables. An Ethernet cable should never die, right? That would be like a 1 in a million thing for it to die. Well, you have enough machines, Ethernet cables just stop working. That happens once in a while. You find, if you have enough machines, you suddenly find that, how MAC addresses are unique? Every machine has a different MAC address. No, because someone in the, factory, ran one that did one run from 1 to 1,000, the next run from 1,000 to 2,000, and that means you had 2 runs that both had a 1,000. And of course, normally no one notices these little errors because what's the chance that those 2 NICs went to the same customer? Well, when you're buying Monday's factory run, we get both of those. So we have to be able to route around failures. Now, let's talk about how failures were dealt with in the first .com era. The first .com era in the early 90s, remember, how did you build a web server? You bought a $25,000 Sun workstation or SGI, and you set it up as a web server, and your traffic came to that web server. 100% of your traffic came to one box. And you bought the most expensive box you could because you needed it to be reliable. And the more expensive machines had the high availability features and stuff. So, yay, $25,000 on a machine. The problem is that when that one machine went down, of course, you were not happy. So, people set up, you had a great idea, I'll get a second machine, and I'll send all my traffic to one machine, and if that goes down, I will switch the traffic over to the other machine. There are various ways of doing that. Some smarter people then started selling a load balancer. So the traffic hit the load balancer, which in this case is a yellow triangle, and half of your traffic went to each machine. And now, if one machine goes down, the load balancer starts sending 100% of the traffic to the machine. So these are your basics of load balancers. Of course, you saw this. You saw great reliability, and I could take a machine could fail on mistake, or I could take it down on purpose for software upgrades, and users are still getting service. But what your boss saw was he just spent $50,000 and you're only using half of the capacity. And he said, hey, that, economically, I don't like that, I don't like that. So your boss says, why don't we just run both at 100%? And you say, well, that's, okay, boss, but then when one of those machines dies, we're going to be sending 200% for one machine, and that's not going to work really well. I mean, you could manage it, like, if you have to do a software upgrade, you'd make sure it'd be done at Sunday morning at 4 a.m. when you just don't have a lot of traffic and that one machine can handle 100%. But then the late 90s happened. Actually, after the first .com crash, things started coming back. People like Jim Gray and people at Stanford and Berkeley started writing papers about, instead of buying the most expensive Sun box we could find, instead we should buy these dirt cheap PC servers. Now, remember in the early 90s, dirt cheap PC servers didn't really run Unix. I mean, they ran Linux sort of, but Linux wasn't stable enough back then. But free and open source operating systems brought good operating systems to these cheap hardwares. Now, the problem is that a $2,000 server, it's not as fast as a $25,000 server, but we can buy lots of them. So what do? We set up the load balancer to load balance across, say, 20 machines, or 25 machines. We've still paid $50,000, but now when machines die, our boss says, well, now you're only wasting 20% or 10% instead of 50%. So economically, this just makes more sense. And this is really what drove the second .com boom. The fact that we could do massive parallel computing using dirt cheap hardware. And it all happened because Moore's law was driving the cost of hardware towards zero. From 25,000 to 2,000, it's trending towards zero. And free and open source software was driving the cost of software from expensive down to zero. Think about it, in the first .com boom, we were, for every darn server, we would buy an Oracle license and a IIS license and a Windows license or a Solaris license. That was expensive software. Open source, it happened so fast we hardly noticed it, but really it happened over 15 years. We hardly noticed it. That the cost of the hardware is trending towards zero, software is trending towards zero. What's left is rent and power. So now you understand why Google does all these green computers. And when you're running multiple applications, you get even more gooder economics. So say we have 3 different applications, application blue, red, and green. Instead of having one machine for each application, be it the spare machine, we could have a spares pool. And when we have an outage in the blue application, we grab a machine out of the spares pool, load it as a blue application, and we're back up and running. The second machine, similar. Make that spares pool machine a green machine. So that's the economics of large web farms and why things are so different in this second .com boom. But the Google founders are always notoriously cheap. If you remember, before Google was a company, it was 2 graduate students at Stanford University, and you did your searches at google.stanford.edu. And this was the actual compute cluster. It was every borrowed machine they could find. And the disk enclosures were built out of Legos because Larry loves playing Legos. When they started a company, yeah, would you consider this a best practice? I see a couple people. When we became a company and we got that first big contract with the AOL, and we were like, well, how many machines would we need to support the capacity? They tell us, you know, that we're going to have that many hits. Well, we had to build racks of machines, and we wanted to do it as cheaply as possible. So this is what our machines looked like in 1999. It was just a rack of machine, and to save money, why buy a case? I mean, that's like 20 bucks extra on every machine. When you're doing massive computation, if you can save $5 per machine, that's a lot of money. Yeah, if you notice, two things to notice. There's no case. In fact, it's just a plain motherboard. And when they started to sag and short out because they were touching the machine below it, they slid in sheets of cork. Yeah, and if you notice the cabling, look at that great Ethernet cable job. Yeah, that's because in 1999, Google only employed software people. And if you don't employ any hardware people, that's the kind of cabling job. By 2000, we started moving into some bigger data centers. And now, notice, okay, the cabling over there is a little messy, but
and the fan's on.
Yeah,
the
fans,
end.
yeah.
if you notice, okay, that's the punchline. Notice there's a fan there blowing on the back of the machines because the
hardware guys,
machines
not
were
cooling
so
guys.
dense. Because we had hardware guys now, but we didn't have cooling guys, people. And what else? Oh, now these machines have cases because we couldn't make machines fast enough. So, well, actually, I don't know there was some economic issue. We actually leased a bunch of machines. I think it just was able, maybe, I guess you do that when you have a cash flow problem, so I would assume that that's why we did that. But yeah, there's a fan blowing at the back of the machines. Back then, also, data centers, so here's, I think in 3 days, we were able to go from an empty colo to a full colo. Another thing to notice about this is, I'll move it later. Okay, and here's our data center at night.
It's full of stars. Funny lines.
This was back, now I remember, this is back when data centers rented space by the square foot. And so we said, really? No matter how much power we use? And they said, oh, you can't possibly use power. So we said, okay. So boom, 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 boom. And boy, the salesperson that made that contract was like, wow, I got a bonus. What a big contract. And 6 months later, his boss is like, I can't believe you made that contract. Yeah. Okay, so in summary, when you have one box, a failure is bad. And when you have two boxes running at 100%, that's bad but manageable. And if you load balance, it's good, but it's not economically good. And when you have thousands of machines, it's more economical. But now, if you're not automating your system administration, you're screwed because you can't have a sysadmin per 10 machine ratio. I mean, that you're not going to have 100 admins. They wouldn't fit in your room. So. So things must be automated. And software upgrades are the same thing. When you're dealing at this scale, software upgrades, that's just an outage that's planned for. If you've done your homework and automated the hard case, a failure, then the easy case of a planned outage is very easy. Or is the same thing. Okay. So when we're monitoring thousands of machines, we need to tell if the machine is up. And our machines all respond to a simple heartbeat. Actually, our services respond to a heartbeat, which is what we call the health request. So we send a sort of a null query to the web server, and it comes back and says either I'm up, or, well, if the machine's down, we don't get a response to you. But that's not true. We actually have a I'm down response. Now, why would we do that? Well, to do a software upgrade, we tell a machine to play dead, claim to be down. That means the load balancer will stop sending any new queries. And if you wait a couple seconds, all the existing queries will finally finish. And then once the query count is dropped to 0, you know it's safe to power off that machine or do whatever software upgrade you need to do. So play dead, wait for a request to complete, do the upgrade, restart the software. It's still claiming to be dead according to the load balancer, but you can point your web browser right at that machine and do some queries to see if they come back right, make sure the software upgrade worked. And if you're happy with those tests, tell the machine to admit that it's up. The load balancer starts sending real traffic to it, and that's how you upgrade one machine. At Google, we have thousands of machines. So we have to automate this. Developers make packages, it goes through QA, it goes through customer acceptance, that's when SRE takes it, we do our own QA, and then we do the big roll. We upgrade one machine, we upgrade 100 machines, we upgrade 1% of the machines, and if we're not seeing any errors at this point, then we just say upgrade one machine per second, and the system just rolls and rolls and rolls and rolls.
What does SRE stand for?
SRE stands for Site Reliability Engineering.
All right, you're missing it for, sorry.
Is this even for the latest Google CSS update, I guess, for the search page?
Yeah, so the 1 or 100 is called the canary, like a canary in a coal mine. If it dies, you know there's a problem. So we canary software changes, we canary static images. We have a whole big system just for canarying for static images. In fact, when Gmail went out of beta, you know, the Gmail logo had a cache header that was like, cache this for 10 bazillion years. And so when it went out of beta, we actually changed the file name. Because we just thought, you know, I don't know, this could be in some cache, and we really want it to not say beta. Now, I lied. We actually are even more paranoid than what I said in the previous slide. What we actually do for binary updates, say this is for like, we're upgrading Google Maps, which I guarantee the binary is not bin/Google Maps. But you know, Google Maps is running and with some options bar, and then the developers say, oh, we have this new feature we'd like to roll out. We're adding spell checking to Google Maps, which was added 3 weeks ago. So we get the software, and each new feature is tied to a flag on the command line. So first, we upgrade the binaries and disable the feature. And we do the whole rollout, and there should be no changes. And then we do what we call a flag flip. We go to each machine and tell it, So we have a mechanism where we can tell our binaries, this flag just changed. And so then we do a flag code to tell the binaries, now start running, pretending that you were started with new feature equals on. And do sort of a canarying process for that also. So very paranoid. I mean, we send out new binaries and don't enable the feature to make sure nothing changed, and then we enable the feature. So, and of course, once you have good failure management, the upgrade mechanisms are sort of done. Now, what about data center redundancy? That's all about machine redundancy. What about data center redundancy? Data centers do catch fire. Actually, our monitoring is so good that we once called a colo and said, we think you have a problem. They said, no, we don't have a problem. No, we really think you have a temperature problem. No, we really don't have a problem. Okay, look, the machines in the lower part of the rack are a lot cooler than machines in the top part of the rack. You should check to see if there's a fire on the floor above us. And they said, there couldn't possibly be one. They sent someone down to check, and there was a fire in the floor. So, yeah, we do extensive monitoring. So data center architecture, you have the internet, things come to, I'm grossly simplified, but traffic comes to a router or switch, there's a load balancer off to the side, and the switch sends the traffic to a rack, and racks usually have 80 nodes per rack. And our internet connections, so we decouple, we split. There's data centers and there's points of presence. Data center is a building with racks and racks of machines, and a point of presence is where we connect to the internet. Most data centers are also a point of presence, but sometimes we just have points of presence just to connect to an ISP that is, if we think that more connectivity in New York City would be better, we have points of presence there, even though we don't have a data center. And what's being cut off on the bottom is Asia, US, Europe. So we have traffic from different parts of the world, and the traffic is routed to the nearest point of presence. We do that by having a homegrown DNS server. So when you do a DNS lookup of www.google.com, you get back not just an IP address, you get back a large complicated formula looks at where did this query come from, which data center is closest, is that service overloaded and we should send it to another data center, all sorts of computations happen in real time, in less than a millisecond actually, and then you get your DNS response. So that if a point of presence is down, the traffic that was going to that point of presence is now sent to other point of presence. Now, sometimes people have asked me a very good question. They say, no, I'll get to that in a second. Now, maybe the point of presence is up, but the data center that's there is down. In that case, we can take the traffic in and route it on our own internal backbone to one of the other data centers. And that's a really important point, that we can route stuff on our own internal backbone. That's important because not every service is in every data center. So let's say, I don't know, Google Checkout. Let's say Google Checkout is in these 3 data centers. The traffic from Asia goes to that one, US goes to that one, and Europe goes to that one. Now the question is, so the question is, if someone is let's say that this diagrams are a little messy. Let's say someone is between Asia and US. It could be, let's say they're in Africa. In Africa, their traffic, which is better for their traffic to go to the data center that's closest to Africa and then through our WAN backbone, or is it better to direct them through the internet to the nearest data center. So, I think I have a diagram. Yeah, okay, so here is an example. I call this style. Style A is we use DNS to send the traffic from Africa over the internet to Asia, or do we send it to the nearest point of presence for Africa and then use our WAN backbone to get it to that data center? Which one do you think we do?
It's cheaper.
I guess whichever one's working best.
Which one's cheaper? Which one's working best? Well, they both have pros and cons. The first one, with the long haul over the internet, the time it takes for that packet to get there is unpredictable. Could be slow. We're relying on ISPs that could be well run or not well run. They could be overloaded, they could be light loaded. We have no prediction of how long it's going to take that packet to get to us. Remember, speed's very important. But being cheap is also important. So that's great because it's someone else's bandwidth. Style B, send it over our WAN, it's more responsive because we own the pipe, we can control the quality of service, but it's not free. We have to pay for that bandwidth. So what do? Well, we can actually do either one. So for Google Maps, you want the user interface to be really fast. But those map tiles, they fill in the background. You wouldn't notice if we did those best, using style A. So if you look at the URLs on the HTML page for Google Maps, you'll see the ones related to map tiles are a little bit different than the ones related to the user interface elements. So we can really control things.
You can fudge both.
We can do both. Both is better. So once you have good data center failure management, these cool features come in for free. So that's our machines and our data centers. Now let's talk about lots of data. Why do we have, and what time is this? 7 minutes. At 7 minutes? Oh, okay. Well, so that's actually let me skip to, what's the best one? Would people like to learn about, I probably have time for one thing. So how the Google file system works, or how we do the processing data, like a multi-terabyte data sets.
Yes.
File system.
File system? Okay, cool. Or Q&A.
We're just going to ask about
Okay. So how does Google file system work? So you know how a normal file system works. You make a request, open a file, read data, whatever, and that same mechanism sends you back the data. Well, we split our file system into two parts. The GFS master, which is running on one machine, and it just is controlling a lot of metadata. And then the chunk servers are other machines, and they store the file system. Because we're storing terabytes and terabytes of data, we've created what is called a parallel file system. The data is spread out over many machines. So if you have a 16 terabyte file, there's a good chance that each terabyte is on a different machine. And we actually break files down into chunks. The block size of GFS is 64 megabytes. So if a client wants to read a file, it contacts the master and says, I want to read file foo starting at byte 1,000,006 and give me the next 10 million bytes. Well, the master doesn't respond with the data. The master responds, hey, that data is over on chunk server number 1. And or at least the next 64 megabytes is. And then the next bit will be on chunk server 2. The next server might also be on chunk server 1, so we're back there. So the client then reconnects to the chunk server and pulls that data out. The neat thing about this is that things can work in parallel. So if you have 10 machines, or if you have 2 machines accessing the same file, one's reading at the beginning and one's reading at the end, one might be pounding on chunk server 1 and the other's pounding on chunk server 2. So you get twice the aggregate bandwidth. Yes?
Is this only for reading of files? Because I presume that you would have a lot of contention when you're doing reading and writing.
Yeah, so writing is, that's the more difficult part. So when you're writing, the master actually, the master tells the client which chunk servers to contact. No, you send the data once to a chunk. Okay, the master tells you what chunk server to send the data to. Now, which brings up a good point. The data, machines fail, like we've talked about before. So how do you deal with failure in a file system? Well, every chunk of data, every 64 megabyte block is stored on 3 different machines. And so when you write that one block to chunk server 1, the GFS master immediately says, oh, there's a block that's in violation of our replicate times 3 rules. So it starts sending commands to the chunk server saying, hey, replicate this block to you and to you and to you. And you could actually set the replication factor. So you could set it to articles 12, and it's every write is then written one place, but then replicated to 11 other places.
So is it the case that the client needs to perform the write?
The client does one write.
The master, which then tells the client which server to write to?
The client tells the master it wants to write, and is told, okay, here's the chunk server you should send it to. It then sends the data to the chunk server, and then the chunk server will replicate.
So it's purely like a traffic cop direction of the master.
It's purely a traffic cop. It's purely a traffic cop, and to be fast, it keeps everything in RAM. So GFS is not limited on file length, but it's limited on the number of files in that entire file system. Because the file and the metadata, the file name and the metadata is all stored in RAM in GFS.
How do you keep all the metadata servers in sync?
How do you keep them in sync? You hire PhDs that do amazing things with syncing.
Magic, okay.
We're really good at syncing data. Yes?
What happens if the chunk server fails before?
Well, that's why we replicate 3 times. But what if 2 fail?
The client is writing to the chunk server. What happens?
Oh wait, what if the client fails? Or
no, but you're saying the chunk server then starts replication.
yeah.
Any part of this can fail. You can have the metadata
Yeah.
not get back, you can have the handoff not work, and all of it can fail.
Sure, there's a million edge cases, and that's why this is a non-trivial kind of thing. But the nice thing is if you needed to grep a 16 terabyte file, now normally if you did that on a big RAID system, that would take, what, 2 days? Grep, foo, file name. 2 days later it'd be done. Well, the way we do it is we say, well, it's 16 terabytes, and we got 500 machines, so why doesn't each machine start, seek to, 1/500th into the machine, into the file, and search that little bit. And so 500 machines all send requests to the chunk servers, and there might be 500 chunk servers. And if you're lucky, the machine that got assigned that bit of data is also the machine that stores that bit of data. That would reduce network traffic. And so we're able to do a parallel grep. Everyone greps their little part, and then coalesces their data to
Query server.
it's sort of a temporary server, and then they merge, and then they send the result. And actually, that is fundamentally what MapReduce does. MapReduce is a generalized system. Now, we do this for grep. We do this for almost every data processing system we do. We have a system called MapReduce. It's a library you link to. It splits your data into input files. It sends the input files to workers. The workers generate this intermediate data to more workers that collapse the data down and eventually send the output to GFS. We're out of time. So I'll just show you one last thing. When you're running a MapReduce, you get this console web page, and you can actually watch. The red is that, or green is the initial mapping, and then red is that second stage, and you see that the merging is starting to happen. This is a MapReduce on 500 machines, and then it's done. Anyway, look for There's some excellent papers on MapReduce, GFS, all of these different technologies if you go to research.google.com. And of course, I can take questions at the break. Okay, thank you.
Thank you.